So the daily problem is find duplicate subtrees. You can pause to read it. But the idea is that we have this tree we're given, and we want to find all the subtrees that have an identical structure and values. So like 2 with a left of 4, there's 2 of those. And then there's 3 different 4s that's a leaf node. 2 different 1s that are a leaf node, 2 different 3s that are a leaf node, 2 with a left of 3. So how do we go about this? The quick and dirty approach is just to utilize hashing, because the idea behind hashing is if you hash something and then you hash something else that's identical to it, you can find out, hey, I've already seen that, or you can keep a count of all the things you've hashed that have that. And you could say, cool, okay, well, actually, LeetCode's weird little built-in data structure tree node it is hashable. So we could say something like test is set test.add root. And then if we print test and return just anything, then it does work. It doesn't throw an error and say that's not hashable. Unlike if we did something like that, then it will say like, hey, you're trying to hash a list. You can't do that. Which is immediately curious, because the whole idea behind not being able to hash a list is that it could contain anything, and it's pretty meaningless to hash the memory address of a list where its contents could be changing between each hash. And it's similar with tree nodes. And we see that here. So if we hash this, we see, okay, cool, there's this whole big list of stuff. And actually, like, that alone makes this not a great contender for hashing, because that means that it's going to take a hot minute. But also, if we say, let's try and hash like this 2 and this 2. So we're hashing root.left and root.right.left, 2 identical things. And if we do that, we can see, okay, cool, root.left and root.right.left are both in there. Because it recognizes them as just 2 separate identities. So we can't get away with that. We have to figure out how to convert them into something and then hash that. Which is fine, we can do that. So we'll do that with strings. We'll just convert each subtree into a string and then hash it. And it's worth noting we can't really use a set, because we're not returning the number of distinct subtrees or the amount of duplicates or anything like that. We're returning each subtree that is a duplicate or has a duplicate. And it doesn't matter which one you return, but we have to return them. So that kind of means that we can't use a set, we got to use a dictionary. So we're going to have a dictionary, let's call it identity. And what it's going to be is a default dictionary where the key is that serialized string that we hash, and then the value is a list of each node that serializes into that key. Yeah, and then we just fill it up. So we'll have something like define depth first search node. And just to get the general structure down, we're going to build a string somewhere in here. And then we're going to say return the string up so that whatever else calls this depth first search is going to use that string somehow. And then in the end, we're going to say depth first search root and return. Here we want to return not the strings, we want to return the nodes. So it's going to be something in this list, but it doesn't matter which one. So we could immediately just say like list at 0, but only if the length of the list is longer than 1. So we could say something like identity at s at 0 for s in identity. So for each string that's a key in identity, but only if the length of identity at s is greater than 1. And then we're leaving behind all the like this random thing where there's only one copy of this, stuff like that. So we start, a good place to start is to say, let's just get node.val in there. And then we want to add like a little comma or something. If we don't have something like that, then when we're comparing like, oh, cool, 2 and 4, we could have 24 down here. And that single number, that single node would be the same as these. So to delineate between nodes, values of each node, we'll just use a comma. So we'll say that. And then you could have something like if node.left is not none, then add that. If node.right is not none, then add that subtree. But you kind of do actually want to keep track of the null values. So you could include that here, or you could say, or else s plus equals like none or something. But instead, we could just call DFS of node.left and DFS of node.right every time. And then at the top here, just say, if node is none, return none, something like that. And a quick side note, you can use an equality comparer here like this, or you can use an identity comparer. Is and equals are kind of the same here, but the difference is that is comparing identity. So it's comparing like, is this exact object the same thing as this exact object? Whereas this is saying like, does this thing have the same value as this thing? So like if you compare two tuples that are like 1, 5, but they were created separately, like I think it might give different results, stuff like that. Okay, so we got this, and then we'll just say s plus equals that, plus a comma, and then we want to return s, but before that, the last thing we want to do is actually add it to the identity. So we'll say identity at s dot append node. So we're adding node to the list of stuff that s has been derived from. So if we run this, it works great. We can clean it up a little bit because like this is not exactly the cleanest code. So there's a couple of ways you could do it. I'm going to use like, I'll say something like s equals, for the sake of visual clarity for something after, I'll say comma dot split, dot join. So we're going to join together all these elements with a comma, and then we can say string node dot val, DFS node dot left, DFS node dot right. And now it's a little cleaner, and we can see, okay, we're adding the node value first, and then the left subtrees thing, and then the right subtrees thing. This is a pre-order traversal. Oops. Oh. We got to actually make it into a list. There we go. And an interesting thing about this problem, and a very quick way to run into issues, is in what traversal you use. So this is a pre-order traversal. I might get the names wrong, but I don't think so. This is a pre-order traversal. If you did a post-order traversal, that would be node.left, node.right, and then node.val. This works too. This works just fine. But specifically, if you did an in-order traversal, where you tried to say like 4, 2, 1, 4, 2, 3, 4, and like that makes the most sense, that actually doesn't work. It'll work for these, but there are specific corner cases where it won't work. This should, yeah, return a wrong answer. And the problem is that like this post-order traversal for some of these subnodes are similar to some of these other ones. So it throws an error. And that's just an interesting quirk of traversals, is that specifically post-order traversals, you can't serialize them into something that's going to be necessarily distinct from every other structure. Whereas for pre-order and post-order traversals, you can. So as long as you don't have it as node.left, node.val, node.right, or node.right, node.val, node.left, then it's fine and it works. But if you have it as that, you have to do a lot more effort. And you can still have it be distinct, but you have to like delineate a lot more. Like you can't just use commas. You have to use like, this is the left node of this, and this is the right node of this, and this is a leaf node or not a leaf node. So it's better just to use a different traversal. And I think that's the big takeaway with this is traversals and this little fun fact. So hit like if you learned something.